number 3. Did you remember how to draw the sine graph? Because we're determining the area between, here's my beautiful sine graph, y equals sine x and the x-axis from x equals 7 pi on 6 to 3 pi on 2. Okay, so we go 0, pi, and 2 pi as our x-intercepts. So 7 pi on 6 is slightly more than 6 pi on 6, or pi. So I have one boundary right about here. And then 3 pi on 2 is where the minimum happens on my sine graph. So there's my area right here. Oh, I wanted a different color. Here we go. Beautiful. This is where you can bring in your pencil crayons, make your notes so pretty. Okay, so what do we need to calculate? We need to calculate the area of 3 pi on 2, or 2 3 pi on 2. It's funky notation, I know. From 7 pi on 6 to 3 pi on 2 of my function sine x in terms of x dx. So then you have to think to yourself, do you know the antiderivative of sine? Hopefully you do. So the antiderivative of sine is negative cos x, and we're going to evaluate that from 7 pi on 6 to 3 pi on 2. So we're going to plug that in. So we have our area, 3 pi on 2 is equal to negative cos 3 pi on 2, this whole thing, subtract, bracket, make sure you're careful with your brackets, negative cos 7 pi on 6. And now we have to go to that wonderful unit circle and decide what it is that we remember about where we are. So we have, let's just draw that quickly here, cos 3 pi on 2. So we're down here at the bottom. We want the x. So that's 0. That's lovely. Okay. So this one is negative 0, 0. Subtract a negative. So I'm going to make that be positive. These guys right here are going to make that be a positive. And now I'm going to 7 pi on 6, thinking about what those coordinates are. So negative root 3 on 2 and negative a half. I want the negative root 3 on 2. So this is going to be plus negative root 3 on 2. And you're saying I've got an answer of negative root 3 on 2. Now, hopefully you're saying, well, that doesn't make sense for an area to be negative. We know that areas cannot be a negative answer. So what we just discovered that is when an area is completely below my x-axis, so I'm completely below the x-axis here, that my area actually comes out, or the numeric value of the integral, I should say, comes out as a negative value because it's below the x-axis. That's why it's coming out negative. If this was just an integral question, then the answer would be negative. But because I actually am determining area, I actually need to then take the absolute value of that and say that the area up to 3 pi on 2 is equal to positive root 3 on 2 units squared. So the area under the curve there is going to be a positive value. So we have to take the absolutes. So anytime we end up with it lying below the x-axis, we're going to end up taking the absolute value. Or alternatively, okay, we could, I'm having a lot of problems with these colors today. We could look at it as finding the area over an interval in which f of x is negative. So if we know, because we drew our picture, that we're entirely below the x-axis and we know the number is going to come out negative, we could think of it as the negative of that integral, and then you get a negative times a negative, making it a positive. So you would be distributing this negative through. Another way, or a better way maybe to look at this, would be just the reverse, f at a minus f at b. But this only really works if you've drawn yourself a really good picture and you know you're entirely below the x-axis and it's an area question. Okay, it has to be an area question to do this little reverse. Okay, so if we're looking for the area and we know that that area is completely below my x-axis, I can switch the interval around and go f of a minus f of b. Okay, but only use this if you're really confident that you know that to be true. Otherwise, just be careful about how your negatives come out. And of course, never write a negative answer for area. Okay, here we go. One more. Determine the area of the region under cos x. So we have to graph our cos x. So remember, cos starts with its max on the y-axis, sort of drew that well. And it has its x-intercepts be at pi on 2. So this is pi on 2. And I'm going from 0 to pi. So pi is where the minimum happens. Okay, so we've got this area here, and we've got this area here. Okay, so from 0 to pi ends up being 2 sections of my curve. I have a piece above and a piece below. That's okay. Let's see what happens when we go to take the area. So the area up to pi is equal to the integral from 0 to pi of my function cos in terms of x. Okay, so there's my notation. Now I need to perform the calculus. So what is the antiderivative of cos? So the antiderivative of cos is equal to sine. And then I'm going to evaluate that from 0 to pi. So when this happens, I get that this is equal to sine pi minus sine at 0. So what happens? Sine of pi is 0, and sine at 0 is 0. So I get 0. So it's clearly not 0 area. So I went around this route on purpose, okay? The problem is that when you end up with a piece above and a piece below the x-axis, then this subtraction part of them clearly doesn't work. Clearly doesn't work in this case. Why did it come out to be 0? Well, one of the reasons why it came out to be 0, or clearly the reason why it came out to be 0, is because the area above, let's call that area 1, and the area below, I'm going to call that area 2, are exactly the same. Okay, so area 1 minus area 2, if they're exactly the same amount, well, of course, that's going to come out to be 0. So we have to come up with a different way to do this question when we have 2 different chunks. And this is really getting a little bit into the next lesson, 10.2. So there's actually 2 ways that we could attack this question. If I don't know how to do it as 2 separate areas yet, because that's lesson 10.2, I could actually just look at this as symmetry. Okay, so let's say method 1. I'm going to call this method 1. And I'm going to say, well, I notice that it's symmetrical, just the way that they have drawn it, or given me my boundaries, I should say. That's the wrong graph. There we go. Okay, so this piece right here is exactly the same as this piece right there. If I recognize that, then what I could do is just calculate the first chunk from 0 to pi on 2 and double it. So that's using symmetry, okay? So a of pi would be equal to 2 times a to only pi on 2. Okay, so this is using my symmetry. So this would be 2 times the integral from 0 to pi on 2 of my function cos in terms of x. I didn't really need square brackets on that. I could have just left my 2 in the front. So that's equal to 2 times the antiderivative of cos is sine, and we're going to evaluate from 0 to pi on 2. And so we get that this is equal to 2 times sine pi on 2 minus sine 0. Sine pi on 2 is 1, minus sine of 0 is 0, and then 2 times 1 is 2 units squared. So that makes more sense, that I actually get a number for my area, okay, all the way to pi. Okay, the second method would be to do them as 2 separate sections, okay? So method 2 is to look at it as I have this area and I have this area that I need to calculate, okay? So I have 2 different areas. So it's going to be like area 1 plus area 2. And then this gets into our next lesson, where we're going to then have the integral from 0 to pi on 2 as my first area of my cos graph, plus the area of the second section, goes from pi on 2 to pi. Okay, so we've got the first section from 0 to pi on 2, that's this intersection. I should use a different color. 0 to pi on 2. And then I'm going to go from pi on 2 to pi to do the second section. And so the antiderivative of cos is sine. And we're going to go from 0 to pi on 2 for the first one. And then we're going to add it to the second one. And that one goes from pi on 2 to pi. So what happens in this case, okay, is we have sine pi on 2 minus sine of 0. That's area 1. That's the one above. Plus sine pi minus sine pi on 2. That's area 2. Now what I have to know about area number 2 is this is below the x-axis. And because it's below the x-axis, like we learned in example number 3, we have to take the absolute value of this one, okay? So we have to remember that. That's why the diagram is so important, that we draw it accurately. Okay, so sine pi on 2 is 1, minus sine at 0 is 0, plus sine of pi is 0, minus sine pi on 2 is 1, but I have to take the absolute value of that. And that's where this gets me my 1 plus 1, which is 2 units squared. Okay, if you recognize that they are completely symmetrical, then obviously that's the faster method to use, okay? And they're not always going to be symmetrical, which we're going to learn in the second lesson here in 10.2. But it is really important to draw that diagram and notice that some of it is shaded above the x-axis and some of it is shaded below. So we either have to notice that they're exactly the same amount above and below, and then we can use this symmetry method, or we're going to have to split it into intervals. That's this second method here. Okay, we're either going to have to split them in, and this is more common, method number 2, which we'll see in the next lesson, that when we have chunks of area above and below, we are going to have to figure out separate intervals and then add all the pieces together. Yeah, that's cool, hey? All right, what else was I going to say in this lesson? Oh yeah, one last thing. It's really important to notice between the area of a question and the integral. So if I had only asked you to calculate the definite integral of cos x dx, this answer would actually be 0. Okay, so this would be where we would actually go 1 minus 1. It's only when it's an area, okay, the area 2 pi of this guy. Okay, so the area under the curve, that's 2 units squared. So it's really important to notice the difference between, is it an area question or just, I'm just calculating a numeric answer. Okay, it's just a definite integral question. All right, that's it for 10.1. I'll see you in 10.2, but you already know where we're headed.